Hi, my name is Vinay, and in this video we will see the layout of a CMOS inverter using Microwind 3.8 software. So we have seen the schematic of an inverter. This is how it looks like. It's just a pair of PMOS and NMOS. So according to the experiment, we have to make three variants of inverter with the varying sizes of devices. Like in the first version, we need to make PMOS and NMOS of the equal width and length. The length is same for all of them, only the width is varying. So the second version, we need to make the width of PMOS as 0.4 and the NMOS width will be twice of the PMOS. And in the last variant, the width of the NMOS would be half of the width of the PMOS. You can vary the width according to your requirements. Not necessary that what value should be there. It's only the ratio changes. So you can modulate the ratio according to your requirements. So we come to Microwind layout software. So I have set the technology to 45 nanometer. So that is what. So this is what the technology I would be using, 45 nanometer. So you can change the technology from file, foundry, and select the 45 nanometer because I've worked in the schematic also on the same technology. So let's start making it. So the first one I require 0.4, that is 400 nanometer. So I select NMOS, so that is what the current it gives. And again click on this, and this side select PMOS. So this is the maximum current. So place it on the clipboard. Okay. So similarly, you put another PMOS for the second device, and maybe for the third device. Yeah. So all three of them. Yeah. Then the second NMOS is of 800, so that is twice the size of this. So I just place it. Yeah. So that the window is causing me a problem. Okay. So maybe I just place it over here. I click on the move and align it with this one. And the third NMOS would be only 200 micrometer. So that's a small version. So there we have. So here we have all the layouts of it. So I just select metal one and use it for joining the VDD of all of them. So I will be using a common VDD source. So that will be the VDD for all. I short the outputs, and there you are. And I bring a little bit of node, little bit on the outside, so that we can quickly access it. Then I take a MOS kit and short the vertical lines, so that will be PMOS and NMOS joining together. I can even join them horizontally because I will give the same input to all of them, so that I get the same input sequence for all of them. So that will be nice. I can put a VDD, I can put a separate VDD for all of them, or I can join using the metal line. So there are. So the construction is ready. I'm just ready to simulate this. Okay, there is a loading also of 0.1 picofarad. That also we can do it later. So I take a clock signal and apply it to one of the node at the gate. I call it Vin and make the time low as maybe 2 nanosecond, time as 2 nanosecond, rise and fall time as the default values. Assign it. Then I just assign it the output. So this is a V1 inverter output, and call this as V2, and this one as V3. Okay, so there you are. You can change the background color by changing Control W, and it will show in this one neat and nice white background. So we can just simulate. Oh, I forgot to bias the NVLs. So what I can do is I can bias the NVL by I just stretch them and join the NVLs. So I just join the NVL and take a VDD supply and put it on one of the NVLs. Change the color. Let me put 10 something. Nothing comes up. Okay, let me see what went wrong. Okay. Yeah, I forgot to give VDD. Sorry, I forgot to give VDD to the VDD supply, and that was missing. So thereby you can see that all inverters are working. So let's load up them. So I take the capacitor and attach to the output. So let it be 0.1 picofarad, the same as in the schematic. 0.1 picofarad. And anywhere you can attach it, 0.1 picofarad. So it will apply an capacitance with reference to node and the grounds. So there you are. So now you see a little bit of varying effect, because obviously the capacitor plays a role in taking the resistance down. So you can measure the results by clicking on the delay between nodes like V in to V1, and you can reset it. So the rise time, low to high delay, is around close to 300 to 89, and the fall delay, high to low delay, is 172 for V1. And if you select V2, then it is 289 is the rise time, and the fall is 82. So here you can see the rise time of the V1 and V2 is the same, because obviously the width is the same of the PMOS. So the PMOS is responsible for making the output rise. So that is the same, because the same amount of current flows from the PMOS channel. Whereas in this case, the width of the NMOS is doubled. So that's why you see there is a reduction in the high to low delay by half. Let's see for V3. So here again the rise time comes almost the same, 288, whereas the fall time increases significantly because the width of the NMOS is half of the PMOS. So that's why the current is lesser, and it will take more time to pull down the output. So that's what the simulation results tells. You can even see the voltage versus voltage curve for various curves, like for V3, V1, okay, and V2, and all you can see. Okay, so this is about CMOS inverter layout. Okay, thank you very much.